last class I told you that dry etching of silicon can be done by using either a chlorine route or a fluorine route. Okay. Let us now investigate what happens if we use the fluorine route and what happens if we use the chlorine route, and then finally what happens if we use a mixture of fluorine and chlorine as the feed gas. Now, for silicon etching, the fluorine route has been used for a long time, very well understood, everybody knows what is actually happened. So, in this fluorine based etching, CF4 is most commonly used. That is most commonly used. Of course, you can use any other fluorocarbon, that is you can use C2F6 or you can use C3F8 or a newer gas like sulfur hexafluoride SF6 can also be used. So, you can use CF4 or C2F6, C3F8 or SF6. They all behave pretty much in the same way. So, we will focus our discussion with respect to CF4. Inside the plasma, we have this reaction. The high energy electrons, they cause the CF4 to break. Remember, inside the plasma we have very high energy electrons. The electron temperature can actually go as high as 10,000 Kelvin. Okay. So, therefore, it is possible to have a lot of reactions which are not otherwise possible at low temperature. So, this is one such reaction. I have energetic electrons reacting with CF4. In the process, CF3 plus radicals are being created, and most importantly the fluorine F star is being created. F star is actually a neutral reactive fluorine species, and to maintain the charge neutrality I have the electrons again, so that this reaction can keep on happening. Okay. Now, for silicon etching, this is the most important item. Silicon is etched by this free F star. This is the primary active species which is going to etch silicon. And how does it etch silicon? It reacts with the surface atoms of silicon and it forms a volatile product SiF4. This is another very important criteria. The reaction product must be volatile. If it is not volatile, the process will automatically stop. Remember, the reaction product has to be carried away from the site. So, unless it is volatile, it will not be carried away from the site, therefore, the reaction will automatically stop. So, for any dry etching to progress, the reaction product must be volatile. Okay. Now, how can I improve the etch rate of silicon? One possibility is by adding a small amount of oxygen in the feed gas. The feed gas is CF4 or C2F6 or C3F8 or SF6. If you add a small amount of oxygen with the feed gas, then this extra additional reaction is going to take place. I have oxygen atom or molecule, they are going to react with CF3 plus okay, and they are going to release extra fluorine. So, if you have a small amount of oxygen that is going to react with CF3 and it is going to release extra fluorine, and the more fluorine, active fluorine you have, more will be the silicon etching. Okay. So, if I want to plot the H rate versus percentage of oxygen, then it is going to increase like this. Okay. But then it reaches a peak at around 10% of oxygen in the feed gas, and then again it begins to fall. This peak is around 10%. So, the increase is easy to understand. It is because extra generation of active fluorine species. Why then the fall? The fall happens when you have too much oxygen in the feed gas, so that the surface of silicon looks not like silicon but like silicon dioxide. And the H rate of silicon dioxide in this feed gas is much smaller than that of silicon. So, so long as you have a small quantity of oxygen, everything is fine. You have more generation of fluorine species, it is going to facilitate etching of silicon, but not beyond a certain point when the silicon surface starts to resemble not silicon but silicon dioxide, at which time the H rate is going to decrease. Okay. So, from this you see we have actually pointed out a quite important fact, that is the selectivity of fluorine based etching. Selectivity, the most common two things you need to distinguish between is silicon and silicon dioxide, right. And I have already told you that the H rate of silicon dioxide is going to be much smaller than that of silicon when you use fluorine. That is why here you see the H rate is decreasing. If you have actual silicon dioxide, the H rate is going to be much smaller, right. So, you have good selectivity if you use fluorine, because you see the etching is taking place by the chemical reaction, the reaction of active fluorine species with silicon, and its selectivity over silicon dioxide is quite good. In fact, you can realize a selectivity of 40:1. If you use CF4 fluorine based etching, then it is possible to realize a relative H rate of silicon to silicon dioxide 40:1. That is, the etchant will etch silicon at a rate 40 times faster than the rate at which it will attack silicon dioxide. So, you have very good selectivity of silicon over silicon dioxide. Okay. But whenever I have good selectivity, the next question automatically comes, what about the anisotropy? Here the fluorine based etching is found to be severely limited, because the reaction is spontaneous and vigorous. That is why the H profile is going to be absolutely isotropic. So, by fluorine based etching you have isotropic etching, but it is selective. You have good selectivity, but you have poor anisotropy. The same feed gas can be used also to etch silicon dioxide and silicon nitride. Of course, the etch rate of silicon dioxide will be much smaller than in case of silicon, but it will still etch silicon dioxide. Okay. How can we improve the etch rate of silicon dioxide? One possibility is again by putting oxygen, putting a small amount of oxygen, just as in the previous case. You will have extra generation of active fluorine species and that will etch silicon dioxide. The problem is, in this process I cannot get any selectivity over silicon. In fact, you see, most commonly what do we have to do? We have a silicon dioxide grown on top of silicon and we would like to open a window in that silicon dioxide, that is we would like to preferentially etch that silicon dioxide, but we want the etching to be stopped when it encounters silicon, isn't it? So, therefore, using this feed gas with small amount of oxygen is not going to help us, because the etch rate of silicon will be much faster. So, I cannot get any selectivity. Instead of that, therefore, what is done is this. You use a small quantity of hydrogen along with Sio4. So, what will hydrogen do? Remember, CF4 inside the plasma, it gave rise to CF3 plus active fluorine species. Hydrogen is going to suppress the formation of this active fluorine species, so that you have okay. So, you have suppressed the formation of the active fluorine species, therefore, etching of silicon will be suppressed. Fortunately, silicon dioxide is also etched by this. Right? So, the etching of silicon dioxide will progress, whereas the etching of silicon will get suppressed, and by doing so it is possible to obtain a selectivity of silicon dioxide over silicon as 35:1. In the previous case, when we added oxygen to the feed gas, it was possible to selectively etch silicon. Silicon was getting etched at a rate 40 times faster. Now, by adding hydrogen, it is possible to etch silicon dioxide at a much faster rate, 35 times faster than that of silicon. So, you see, dry etching I have so much flexibility. I use the same feed gas, I only modify the composition of the feed gas slightly, so that I can etch either silicon or silicon dioxide with very good selectivity. Okay. The other thing is, of course, etching silicon nitride. Next to silicon dioxide, the dielectric mostly used in VLSI technology is silicon nitride, and we would like to etch silicon nitride. Okay. So, silicon nitride is also etched by this active fluorine species. Fluorine reacts with silicon nitride again to give rise to silicon tetrafluoride SiF4, and nitrogen is released in the process. So, now the question is whether you want to have selectivity over silicon or selectivity over silicon dioxide. It may not be possible to etch silicon nitride with good selectivity over both silicon and silicon dioxide at the same time. So, depending on whether your substrate is like this, that is if you have a structure like this, the top layer is silicon nitride, then I have silicon dioxide, and underlying is the bulk silicon substrate. In that case, you want, when you are etching silicon nitride, you want good selectivity over silicon dioxide. Okay. On the other hand, if you simply had silicon nitride and silicon, then you would want to have good selectivity over silicon. So, depending on what your substrate is like, you should choose the feed gas composition. Okay. So, you have two options. You can either use the feed gas with a little bit of hydrogen, just as in this previous case, okay, so that the formation of this active fluorine species is suppressed and therefore silicon will not get etched. So, you will have good selectivity over silicon, good selectivity of etching silicon nitride over silicon, that is one possibility. So, if you have this kind of a composition, use CF4 plus hydrogen, that will give you good selectivity over silicon. If however, you want to have good selectivity over silicon dioxide, in that case you have to use probably you should use a feed gas with a little bit of chlorine in it, chlorine or ClF3 in it. Okay. So, when ClF or ClF3 is the active species, then silicon dioxide is not attacked. So, you have good selectivity over silicon dioxide. In fact, the feed gas composition used in such cases will usually be NF3 plus chlorine, which will give rise to the active species of ClF or ClF3, that will not attack silicon dioxide, but it will attack silicon. That is what I meant, that you cannot have good selectivity over both silicon and silicon dioxide at the same time. You can choose a feed gas composition which will give you, which will preferentially etch silicon nitride with respect to silicon, or you can use another feed gas composition which will preferentially etch silicon nitride and will not attack silicon dioxide. So, depending on what you want, which of these two structures you have, whether you want to have good selectivity over silicon or silicon dioxide, you should choose the feed gas accordingly. So, this is actually the fluorine based etching of silicon and silicon based compounds. We have talked about etching of silicon, silicon nitride as well as silicon dioxide. The common feature is this: silicon is etched very easily using CF4 feed gas. You can improve the etch rate by adding a little bit of oxygen, okay, so that you have more generation of active fluorine species which is going to react with silicon and give SiF4, which is a volatile product. The same feed gas will also etch silicon nitride and silicon dioxide, but with lesser degree. So, if you want to have selectivity of etching of silicon dioxide or silicon nitride over silicon, you should use this feed gas with a little bit of hydrogen. Hydrogen will suppress the active fluorine species. It will form HF and therefore, it will suppress the formation of active fluorine species and therefore, the etching of silicon will be hindered. But the etching of silicon dioxide and silicon nitride will go on, and in the process it is possible to have a high selectivity. Like I told you, in case of silicon dioxide over silicon, it is possible to have 35:1. Same thing also holds good for silicon nitride. But the problem is when I want to obtain selectivity of etching silicon nitride over silicon dioxide. In that case, I may have to use a different feed gas, something like NF3 plus chlorine, where the active species of etching will be CLF or CLF3, which will not attack silicon dioxide, but it will etch silicon nitride. But remember, if you use these feed gases, then you do not have selectivity over silicon etching. Okay. This is the fluorine based etching of silicon. Let us now talk about the chlorine based etching of silicon. In chlorine based etching of silicon, there are a few ground rules. First ground rule is that chlorine will not spontaneously etch undoped silicon, or we can say that the etch rate will be extremely small. So, undoped silicon cannot be etched in chlorine, just in chlorine. I do not mean plasma. What I am trying to say is it cannot be etched spontaneously in chlorine. There is no spontaneous chemical reaction between chlorine and undoped silicon. So, that is the first ground rule. No spontaneous reaction between chlorine and undoped silicon. Rule number 2, however, in presence of energetic ions, when I have energetic ion bombardment, then the reactivity of the surface can be made sufficiently high so that it reacts with chlorine. I have already mentioned this in the last class, that is the energetic ion enhanced etching. If we have energetic ions bombarding a particular surface, the reactivity of that surface can be modified so that maybe in the absence of plasma the surface would not have reacted, with the feed gas, but now the reactive surface is going to react. Okay? So, it is possible to have energetic ion enhanced reaction. Energetic ion enhanced reaction is possible. And point number 3 is, however, all these are applicable to undoped silicon. If I have heavily doped silicon, then chlorine is going to react spontaneously with that surface. Heavily doped N-type silicon will react spontaneously with chlorine. Okay? So, you see, chlorine actually offers you a lot of possibilities. First of all, if you have intrinsic or undoped silicon, you can have energetic ion enhanced reaction, in which case you will have very good anisotropy and also good selectivity. Okay. On the other hand, if silicon is very heavily doped, then chlorine is going to react spontaneously, right. In that case, you would expect that the etching profile will be isotropic. Anisotropy will suffer, because it is going to take place by spontaneous chemical reaction. You can even here you can get anisotropic H profile by using an inhibitor along with the feed gas. And the very common inhibitor is C2F6. Use C2F6 with chlorine. C2F6 is going to form an inhibitor film on the sidewalls. On the sidewalls, this inhibitor film is going to remain. On the surface which is bombarded by the energetic ions, the film will get removed. So, again it is possible for you to have anisotropic H profile. Okay? However, here the feed gas composition has to be carefully monitored. That is, there should be sufficient C2F6 to form the inhibitor. Otherwise, you will get isotropic profile. So, you see, even here you have a lot of flexibility. By using the same feed gas with varying amount of relative percentage of chlorine and C2F6, you can get isotropic or anisotropic profile. So, altogether chlorine offers you much more possibility than fluorine. In fluorine based reaction, as I said, we are always stuck with very poor anisotropy, because the reaction is so vigorous, it is not even possible to have any inhibitor forming mechanism. so vigorous reaction that nothing works. You always get isotropic profile. In contrast, chlorine offers you a lot of possibilities. Okay. And particularly this is a very interesting reaction. See, I am using C2F6 and chlorine. Okay. Now, silicon dioxide does not get etched by chlorine. Silicon dioxide does not react with chlorine, does not get etched by chlorine. But you know, your native silicon, the basic silicon wafer will always have some native oxide present on that. So, if you try to etch it simply using a chlorine plasma, etching may not be very fruitful, because you have some traces of oxide present on the surface. That oxide is not getting etched, therefore etching cannot progress. So, even there this feed gas is going to help, C2F6 plus chlorine. How? C2F6 can etch silicon dioxide. Remember, I told you that you can use CF4 or C2F6 or C3F8. So, that will etch silicon dioxide. So, remember, C2F6 therefore serves a double purpose. It does two jobs. One job is it etches silicon dioxide, the native oxide that is always present on any silicon surface. And secondly, it forms inhibitor film, so that you get very good anisotropy even when you are etching heavily N-type silicon. You can of course play with a combination of chlorine and fluorine. In that case, usually ClF3 and chlorine, ClF3 and Cl2, these are used as the feed gas. That is, the feed gas has two constituents, one is chlorine, the other is ClF3. So, I can have a fluorine plus chlorine based etching. Feed gas is going to be ClF3 plus Cl2. What you have is, you start with pure ClF3. So, ClF3, pure ClF3 is going to give you most fluorine, okay. Mostly the active species obtained in a ClF3 plasma is going to be fluorine. So, the H profile will be isotropic. Fluorine based etching, I am going to have isotropic profile. You start increasing the percentage of chlorine slowly. What will happen? Slowly the anisotropy in the profile will start increasing, right. So, actually if I plot dHdV, dHdV is the rate of etching of the horizontal surface relative to the rate of etching of the vertical surface. dHdV, okay. You want dHdV to be you want the horizontal surface to be etched not the vertical surface, right. Therefore, you want dHdV to be as high as possible, right. So, if I plot it as a function of the percentage of ClF3 in the feed gas, then it is going to increase like this. So, as I keep on increasing the percentage of chlorine, the rate of ratio of dHdV approaches 1, about 0.8. That is, here I have more or less isotropic doping profile. When I have the feed gas composition mostly ClF3, nearly 100% ClF3, I have an almost isotropic H profile. As the percentage of ClF3 is slowly decreased, it falls, right. The H profile can also be shown like this. Let us say I have silicon surface, okay, and I have a very small percentage of ClF3. Then I have an almost vertical profile like this, almost vertical, not exactly but almost. That is when I have 6% of ClF3. Let me increase this percentage of ClF3 from 6% to let us say 30%. What am I going to have is you will find undercuts, right. If I go to even higher, say 50%, so as I increase ClF3 percentage, I am going to have more and more severe undercut problem because the etching is going to be isotropic. Okay. So, basically you see silicon etching, therefore, you can do by using either chlorine or fluorine unless you are particular about the H profile. CF4 is most commonly used. Okay. If however, you want to have good anisotropy, you have to use chlorine based etching or a combination of chlorine and fluorine based etching, because simple fluorine based etching can never give you an anisotropic H profile because of its spontaneous and vigorous reaction. Chlorine offers you more flexibility. There are possibility of energetic ion enhanced reaction as well as by suitably modifying the feed gas composition, you can have inhibitor formation, so that also anisotropy is improved. Okay. The other material that I want to etch is the metal, aluminium. Okay. Now, aluminium does not get etched by fluorine at all. You know why? Because aluminium fluoride is not volatile. Remember, for dry etching, this is a prime concern, whether the reaction product is volatile. Unless the reaction product is volatile, it cannot be used for etching. So, aluminium is not etched by fluorine because aluminium fluoride is not volatile. So, for etching aluminium, we again use chlorine. Chlorine can etch aluminium spontaneously. You can have isotropic etching. If you want to have anisotropic etching, then you should use an inhibitor forming substance in the feed gas. Okay. Also remember, like silicon, aluminium has a great affinity for oxygen. In fact, aluminium has a greater affinity for oxygen. So, aluminium, whenever you have aluminium film present, the surface is always covered with oxide. Okay. And like silicon dioxide, aluminium oxide also cannot be etched by chlorine. So, aluminium is etched by chlorine. It is a spontaneous reaction, therefore, the etch profile is isotropic. Aluminium oxide, however, is not at all etched by chlorine. So, when you are etching aluminium in practice, you must have a feed gas which will be able to etch not only aluminium, but also aluminium oxide. At the same time, if you want to have an isotropic etch profile, then your feed gas must contain an inhibitor forming substance, because otherwise it is going to be isotropic. The etch profile is going to be isotropic, right. This dual purpose is served mostly by using BCl3 or SiCl4. Or sometimes even carbon tetrachloride. They serve the dual purpose, that is, they etch the aluminium oxide as well as they form the inhibitor film to provide anisotropy. The other material that you are interested in removing is photoresist, and I have already mentioned when we are talking about barrel reactor that photoresist can be very easily removed by simply burning it up in oxygen plasma. So, for photoresist removal you do not need any of these fancy feed gases, all you need to have is an oxygen plasma and photoresist can be ashed, that is called ashing of photoresist. The other point that I want to mention is, We have talked about reaction rates, how the feed gas composition is going to affect the reaction rate and all that. But there is another factor which is also going to affect the reaction rate, and that is called the loading effect. It is found that if you put too many samples inside the etching chamber, then the etch rate goes down. I put one sample, one wafer in the etching chamber, okay, and I measure the etch rate after operation in a particular ambient condition. Then keeping the ambient conditions identical, if I put 5 wafers, I will find that the etch rate will become less. Maybe not 5 wafers, but if I put 50 wafers, I will definitely find that the etching rate is becoming less, and this is called the loading effect. If you load the reactor chamber more, the etch rate is going to be less. Particularly when you have spontaneous vigorous chemical reaction like fluorine based etching of silicon, this loading effect is quite a dominating factor. Okay? So, how to minimize the loading effect? Obviously, for mass production we would like to minimize the loading effect, and this can be minimized simply by keeping the reactor area much larger compared to your total sample area. The ratio of reactor chamber area A to the wafer sample surface area AW must be very large. That is, in other words, your chamber should be big. The bigger your chamber, the less is the loading effect. Okay? So, the loading effect can be minimized by simply keeping the chamber area much larger. This is particularly important when you have a mass production line where it is important that you can etch a large number of wafers without having to sacrifice the etch rate. So, there it is very important. And the other factor, of course, as I told you, that loading effect is particularly dominating when we have a very spontaneous and very vigorous chemical reaction, for example, fluorine based etching of silicon. Now, so far we have talked about dry etching, or in other words we can also call it plasma assisted etching. Okay. So, dry etching or plasma assisted etching, they are almost synonyms. Okay. Now, plasma, in all these discussions we have used plasma to etch the sample surface. Somehow the plasma has assisted, either by generating the active chemical species or by energetic ion bombardment. Somehow plasma has helped in the etching reaction. So, just as plasma can be used for etching reaction, plasma can also be used to do exactly the opposite, that is the plasma assisted deposition. And the reactor designs are almost identical, if not identical, they are very similar. You have the same two parallel electrodes, you have a chamber in which you produce the plasma. The only difference lies in the minute details, that is what should be the ion bombardment energy, what should be the sheath potential, what should be the pressure of the chamber. Except for these minute details, a plasma etching chamber, a plasma etching reactor is very similar to the plasma deposition chamber. And plasma deposition is a process widely used today for deposition of dielectrics like silicon dioxide and silicon nitride. So, that is going to be our next topic of discussion.